Oh, hey everyone. So today I'll present one proof of the sine addition formula, which is not very common, I suppose. So if you recall, the sine addition formula, it gives us a way to find the sine of the sum of two angles given the sines and cosines of each of the individual angles. So basically, if you have like a right triangle and another right triangle, let's make that 90. Then if this is 1, if the length of AD is 1, then the sine of alpha plus beta is going to be BE, DE. So DE is 1 times the sine of alpha plus beta. And the formula claims that this is just sine alpha cos beta plus cos alpha sine beta. So we'll prove that today with Ptolemy's. So one way that might be natural to get started trying to prove this is just drawing, a regular right triangle. Let's make the hypotenuse 1. Maybe we'll make one right triangle have an acute angle of alpha, and the other one share a hypotenuse and have a acute angle of beta. And let's just label this like A, B, C, D for the vertices. So if you look at this quadrilateral ABCD, its opposite angles add up to 180. So it's cyclic. 90 plus 90 is 180. So opposite angles add up to 180. So it's cyclic. So there's some circle that passes through A, B, C, and D. And then we can label, this is going to be sine alpha. This is going to be cos alpha. It's going to be cos beta for AD, and CD is sine beta. So you might notice if you apply Ptolemy's to this, that you get the exact expression for the sine addition formula. So by Ptolemy's, the sum of the product of the opposite sides, so sine alpha cos beta plus cos alpha sine beta equals the product of the diagonals, so AC times BD. Ptolemy's, if you recall the statement, says that AD times BC plus AB times CD is the product of the diagonals. That's what Ptolemy says, and it only applies for a cyclic quad. So now, this looks like exactly the expression for sine alpha plus beta. So we might think, oh, maybe there's a proof of the sine addition formula hidden in this diagram. So, I mean, how are we going to get a sine of the angle alpha plus beta, right? Well, I mean, here's the angles, alpha plus beta. We might as well drop a right triangle here. Let's make this point E, the foot of the altitude from D to AB. Then the sine, so the length of DE is going to be the hypotenuse length. So DE is the hypotenuse length AD times the sine of alpha plus beta. So let's see what this gives us, right? So, we can simplify this to be DE. So the length of AD, we said that was cos out beta, right? Cos beta. And then this is sine of alpha plus beta if we just plug in what we had here. Also, by Ptolemy's, we can see that the expression for the supposed expression for the sine of alpha plus beta is AC, which is 1, times BD, which we'll just write as BD for now. So let's look at our cyclic quad ABCD. Because this subtends the same angle as that, this is also beta. And then because these are parallel lines, this angle EDB is also beta. So what we could see is the red line times the cosine of beta is DE. So let's see here. Another expression for DE is using triangle BED. Here in triangle BED, the hypotenuse BD times the cosine of the angle beta is going to be DE, looking at that diagram. So let's express BD we found was this expression using Ptolemy, so let's just plug that in. So BD is and then we have a cos beta here. So now we have two expressions for the quantity DE, so we can equate them. So if we equate these, we'll get cos beta sine alpha plus beta equals this expression that we got from Ptolemy's times cosine beta. We can see we have a cosine beta on both sides, so those will cancel. Hence, sine of alpha plus beta is this expression, and that's what we wanted to prove. So that's a good place to stop for today.